So, okay.
Oh, right. I forgot to say, we will record the meetings so people can also view it afterwards. The session with the students and postdocs, we won't record. That should be more private. Go ahead.
Awesome. So kind of following on Dan's sort of, vision for this introduction / tutorial, my goal is really to give a little bit of a sense for the way I think about some of the questions that David is interested in and that David will touch upon in his talk, but at a very, very broad level to kind of introduce it sort of just so that one has a feeling for sort of and a foothold for what the flavors of questions are, and maybe kind of a sense for the bigger picture. So for people from all fields. Good. So it turns out that these days, David is a quantum dynamics guy. So the way I sort of thought I'd structure the tutorial is in the context of questions that our center, the CIQC, is interested in thinking about. And in particular, I wanted to frame it in the context of thinking about quantum dynamics for quantum advantage. So all of you have recently certainly been aware of the various demonstrations of quantum advantage from sampling type experiments. So there was a really nice paper last year or 2 years ago now, implementing random circuits using superconducting qubits from Google. And there, the idea for all of these types of sampling problems is very simple. It's premised on the fact that kind of simulating quantum mechanics is generally a hard thing to do. And thus sampling from the output of sort of a wave function given by some quantum evolution is also going to be a hard thing to do. But especially in the context, and also there was a more recent paper coming from Jianwei Pan's group on doing this similar analogous experiment in the context of boson sampling. In the context of these types of sampling experiments, one's often thinking about sort of random circuit type evolution, where one's building up the dynamics of these systems using, for example, random 2-qubit gates and random single qubit gates. But one thing that our team has a particular strength on is the ability to do quantum simulation of Hamiltonian evolution. And this Hamiltonian evolution also, in principle, can serve as a way to generate entanglement and complex wave functions. So the setting that I want us to think about for this tutorial is a very simple setting. The setting is, imagine that we start off with a system of many particles, and we start off the system of many particles in a product state. And then on top of that product state, we explore time evolution using a particular type, class, instance of a Hamiltonian. And the CIQC-esque question that I'd like us to keep in the back of our minds is, for example, are there conditions, or what specific conditions on the Hamiltonian are required to prove that sampling from the wave function generated by the time evolution is actually hard? For example, this question was kind of addressed in the context of random unitary circuits by Boulan, Pfefferman, Nierk, and Vazirani a couple of years ago. But here, I'd really like to think about it, thinking about it from the perspective of Hamiltonian dynamics and not from the perspective of a random unitary circuit. And to start off, so for people from sort of my tribe, I guess this will be sort of a lot of background way of thinking about this, but I hope that this will be useful for people coming from sort of the various backgrounds that are part of the center. And what I want to emphasize is that really, when we think about dynamics, somehow it's oftentimes we think about the general perspectives that most of the dynamics that one gets are kind of similar to chaotic systems, to random unitary circuits. But the emphasis that I'd like to place is really that there are many different classes of quantum dynamics given by different flavors of Hamiltonians. One can have systems, for example, that are disordered, systems that are integrable, where there's in principle an extensive set of integrals of motion that constrain the resulting dynamics. And one can, of course, have the types of Hamiltonians that one's oftentimes most familiar with, which are those that are actually thermal. And what I want to do now is just to walk us through a very, very simple kind of categorization or an example set of classes for this type of dynamics. And in particular, the setting that I want us to zoom into now is a one-dimensional spin chain. Okay, so it's a one-dimensional system of particles where the Hilbert space for the particle is basically equivalent to a qubit. And we think about the Hamiltonians that we can write down as basically being built up of Pauli matrices. And for most of the things that I'm about to write down, we're actually going to think that these spins basically interact very nearby with each other. So they're sort of not talking over very long distances, they're kind of nearest neighbor interactions. And even within this context, I hope that I can explain that, there are, in this simple setting of one-dimensional spin chains, already many different types of Hamiltonian dynamics that can exist. So the simplest, at the risk of writing equations, but I think actually for some subset of the audience who are not, exactly my tribe, I think this will be helpful. I hope this will be helpful. There are Hamiltonians that are integrable and free. So the classic example of this is, for example, the transverse field Ising model. So spins interacting with each other with nearest neighbor Ising interactions in the presence of a magnetic field, say in the x direction. Or the Hamiltonian I've written here is basically the XY model, corresponds to sort of spins kind of polarizing and depolarizing with each other in a nearest neighbor fashion. And this type of Hamiltonian has, one, an extensive set of integrals of motion that constrain the dynamics, but two, it's free in the sense that maybe the computational sense is that solving for the properties of the system, whether they be dynamical or not, scales only as the hardness of that scales as the number of particles in the system and does not have an exponential cost. And the reason for that is really that one can build up wave functions starting from single particle wave functions. Okay. It turns out that there are integrable models that are not free, where as far as we know, integrable models like this Heisenberg model, like the model I've written down here in the Hamiltonian, so it's sort of, the nearest neighbor interaction in terms of sigma dot sigma. So we have XX, YY, and ZZ when one expands this dot product. These types of Hamiltonians are also integrable. And usually in the context of quantum chaos / random unitary circuits / quantum advantage, oftentimes we think of integrability as somehow making the physics of these systems easy, and in particular, making the dynamics of the system easy. And I think that is something that one has to be very careful about, actually. So I think that, in fact, sort of for these types of integrable interacting systems, it is just as hard. I mean, it's not maybe not fully known, but I would suspect that it's just as hard to simulate the dynamics starting from an arbitrary product state as it is for a totally interacting system that does not have this extensive set of integrals of motion. So one can ask a natural question, is it true that one can kind of get quantum advantage even from the dynamics of integrable systems, which normally we think about as not precisely being chaotic or not precisely thermalizing? In both of these contexts, still staying with one-dimensional spin chains, one can add disorder. So, for example, break translational invariance in the system in some way. And this disorder, for example, can lead to the arresting of transport so that the motion of energy or the motion of spin becomes difficult. In the context where one adds disorder on top of an integrable and free system, one gets a phase called the Anderson localized phase. In the context where one adds this type of translation invariant breaking disorder on top of an integrable but interacting system, for example, one can get a many-body localized phase. Finally, I think the class of Hamiltonians that one's quite familiar with are those that are, I guess these words sometimes are used synonymously, although each of them I think has its own, subtleties. Thermalizing, chaotic, or scrambling Hamiltonians. So an example of this that I've written down is the one-dimensional mixed field Ising model. So if one adds a longitudinal field on top of this transverse field Ising model, one gets a model that naively has thermalizing dynamics for the system. I just wanted to end with a little bit of a nod to some very, very recent developments in the context of looking at Hamiltonian dynamics. I should emphasize that out of these 6, this is the only one that's not a 1D spin chain. There's a model going under the moniker of the Sachdev-Kitaev model, which exhibits a type of dynamics called fast scrambling, which is conjectured to saturate bounds on how fast quantum information can move in these systems. And again, one wonders whether or not saturating this bound or, appropriating this bound can be thought of in the context of advantage, or one can say something sharp about that. So with that, let me just very, very quickly give a sense, so I've emphasized that even in this very simple setting of a one-dimensional, basically nearest neighbor interacting spin chain, I think about Hamiltonians as having lots of different classes. So asking the question of, does a particular property of a Hamiltonian allow one to make claims about hardness from the perspective of computational cost, I think is interesting. There are also physical ways to distinguish these types of Hamiltonians. Perhaps one that's familiar to a lot of this audience is this notion of looking at how entanglement grows. So for example, taking a bipartition of a system and asking how much entanglement there is in the left and the right-hand side. The thing that I want to emphasize is that in principle, one can distinguish some of the different types of disordered Hamiltonians from those that are thermal. But there were more classes in sort of what I wrote down in the 6 classes that I wrote down a little bit earlier than just this distinguishing. And in fact, many of those features are sort of lost if one only looks at the behavior of entanglement entropy. I should emphasize that, I'm on a semi-log scale over here. So because the x-axis is being logged, this really is a very, very slow growth of entanglement. So systems that are thermalizing typically have ballistic growth, and models like the Satyevich-Kitaev model have an even faster growth. Recently, there's been ideas to tease apart, for example, these different classes that all exhibit this kind of ballistic growth of entanglement. So maybe entanglement is not quite powerful enough to distinguish all of the different types of Hamiltonian dynamics. And so another thing that's come online is this idea of looking at the way operators spread, and in particular at looking at higher point correlation functions called out-of-time ordered correlation functions. And the intuition there for these types of diagnostics, just to give a flavor, is that one can maybe imagine an initially local operator. Under some generic Hamiltonian dynamics, that operator might spread. It might exhibit a natural light cone. And one can ask, for example, if one at some later time perturbs at some other site P and attempts to time evolve backwards, the question of how chaotic the Hamiltonian is mapped onto how much this local perturbation at a later time spoils the backwards time evolution of this operator returning to an initially local site. And that diagnostic is called the out-of-time ordered correlation function. It allows one to distinguish some of the subsets of Hamiltonian dynamics that were not able to be distinguished by entanglement alone. But even then, it doesn't allow one to distinguish them all. For example, integrable interacting systems and non-integrable systems, we think exhibit very similar behavior from the perspective of this type of a correlation function. So, I think that the take-home view that I wanted to get across here is really that, Hamiltonian dynamics are much richer than just random unitary circuits. And I think our team has access to many different classes of Hamiltonian dynamics that may be interesting to ask questions about in the context of thinking about things like quantum advantage or the computational cost, for example, of simulating some of these systems in sort of a provable way. With that, let me just emphasize that there are lots of open questions at the interface between theory and experiment. And especially, I think, interactions between members of the team will be able to help us answer some of those. There are some really nice experiments. Actually, I think this is showing band populations. This isn't exactly dynamics, but there are some nice examples already of this, kind of idea of interacting versus non-interacting experiments and looking at the dynamics of these systems under different parameters that control the dynamics, for example, the driving frequency. So if there are questions specifically related to the tutorial, I think Dan might have mentioned this, feel free to put them in the chat as well. We'll sort of hopefully answer them as we go on, or maybe in the discussion section as well. And with that, let me just introduce our speaker. So it is my pleasure, certainly, to introduce my good friend and colleague, David Weld, as our inaugural colloquium speaker. As a kid, supposedly, David had an inexorable love for Legos. And as he puts it, this has led to a career as a physicist with a goal of building bigger things with larger and fancier blocks. Turns out for him, the fancier is correct, but the larger is wrong. He sort of went much smaller. David did his PhD at Stanford, doing beautiful work on precision force measurements with a goal to explore constraints on deviations from Newtonian gravity. He was then a postdoc at MIT before joining the faculty at UC Santa Barbara in 2011. He's garnered lots of prizes, but just to mention a few, these include the Sloan Fellowship and the Presidential Early Career Award for Scientists and Engineers. Broadly speaking, David's research group uses quantum degenerate gases to explore lots of different quantum mechanical phenomenon, and his recent interests have included a variety of topics ranging from non-equilibrium quantum dynamics and the simulation of ultra-fast phenomena to periodically driven quantum systems. We are looking forward to your talk, David. So I'll stop sharing.
So thanks so much, Norm, for the very nice intro and the super interesting tutorial at the beginning as well. So let me try to share my screen. Is this visible to people? Okay, awesome. I don't think I can see the chat while I'm doing this. So maybe Norm, you can alert me if there's things that come up in the chat window. So thank you all for having me. I'm very excited for the CIQC to get going, and I'm excited for this colloquium series, in fact. While I was waiting for the requisite 10 minutes to elapse at the beginning of this meeting, it occurred to me that starting a colloquium on Berkeley time is equivalent almost exactly to starting it exactly on time at the center of the solar system. So this, I think, is a very symmetrical practice, and I support it, and we'll try to import it to our satellite campuses. So what I wanted to talk about today is, as the title says, kind of an overview from the atomic perspective of experimental quantum information processing platforms. And the talk kind of comes in two parts. First, I'm going to, from the perspective of my tribe, as Norm says, which is the tribe of experimentalists, kind of contextualize the role of atomic physics, and in particular neutral atoms, within the CIQC and within quantum information processing efforts more broadly. So this is going to be, I really tried to make it a true colloquium intro, very broad, talking about the whole ecosystem of quantum information processing, trying to maybe make people angry enough to ask interesting questions or something. And then in the second half of the talk, I'm going to be moving into more the kind of thing that Norm was introing, which is a discussion of dynamics. And I think Norm really eloquently put the ways in which dynamical experiments in the NISQ era offer a possible route to achieving quantum advantage with tools that we have now and coherence times that we have now. So, so I kind of organized my talk around a few different questions after consulting with Norm and and Charles and Emily and Dan and the other organizers. And I want to go through these questions before I begin the two parts of the talk that I mentioned. So things that I think we can be thinking about at the CIQC are questions like this. So we have a certain menu of experimental techniques that are available within our institute, and there are some others as well. And it's probably good to try to lead the receiver a little bit and think about how that's going to change over the next 5 to 10 years. What we think the next really exciting platforms will be, because this isn't something that appears to be static on that time scale. In particular, the thing that I can maybe address is where neutral atoms fit into this ecosystem. And Norm touched on that briefly as well. And a related question to that is, what's the future of this idea of quantum simulation? Not gate-based quantum information processing, but quantum simulation, Hamiltonian simulation of the type that Norm described in his introduction. More generally, I think it's an interesting question to think about what this institute is, as Dan said at the beginning, contains a very broad range of specialties and of different research interests. And I think right now at the beginning, it's an appropriate time to be thinking about what kinds of topics can actually bring people together from opposite ends and try to unite a few of these different tribes within the Institute. And a question which I think actually Norm alluded to and Dan also alluded to in the chat just now is maybe one of these questions that people from different walks of life within the Institute can talk about is, if you want to build a quantum device which can be proven to be doing something challenging and interesting to solve a hard problem. In other words, what counts as hard and what counts as a problem? And I think this is almost as much a cultural question as it is a scientific question. So it's something that I think discussion among people from different backgrounds will be helpful in elucidating. Okay, so but the first part of my talk is, as I said, an extremely high-level tour of experimental quantum information processing platforms, just talking about some, one atomic physicist's view of how this landscape looks right now and some of the places that I think are ripe for further investigation. So the first thing to say about quantum information processing platforms is everything counts as one, because everything is quantum mechanical as far as we know. Not only, computers, obviously semiconductors are well known to be quantum mechanical objects, but also knives. So in some sense, it should be the case from an experimentalist point of view that the features that we're trying to leverage in this institute, entanglement and superposition in particular, should be everywhere. And they kind of are. But using them, doing something useful, requires not only that entanglement and superposition be present, but that they be isolated from other degrees of freedom in the universe, and that they be controlled. So there's kind of this cartoon picture of an experiment of the type that our institute is interested in, which looks like this. You take some subset of the whole universe, which we think has a wave function and is quantum mechanical entirely as far as we know, cut out some piece of it, protect it from all the rest of the universe, which is trying to entangle with it and mess up the dynamics and give you evolution other than what you want. And then reconnect it to a little bit of the universe, like your knob on your apparatus, so that you can manipulate it and do the experiments you want to do. So that this is sort of, these two requirements of isolation and control are the two desiderata that are in tension for different quantum information processing architectures, because these obviously pull in slightly different directions in terms of designing a platform. So you have to balance isolation and control. And you can make different people, I think DiVincenzo was one of the first, have made lists of things that you want in a reasonable quantum information processing platform to try to do these address these hard problems that I talked about in the first slide. And here's here's my list, which is largely adapted from DiVincenzo's with one addition of the things that you would want in a quantum information processing platform. So you want it to have a robust representation of quantum information, maybe spin a half system or something. And the word robust there is the entire, that corresponds to the need for isolation. It's robust if it's not coupling to the rest of the universe and decohering. You want to be able to reliably prepare it, transform it according to various gates, and then measure the output. And that corresponds to the control aspect of what we want. And finally, the added one here is you want a qubit platform that uses techniques that humans are already good at. A lot of experimental physics, maybe all of experimental physics, I would say, is fundamentally parasitic on past industrial investment. So a good chunk of modern condensed matter experimental physics is an outgrowth of, byproducts of the semiconductor industry. In atomic physics, we're entirely dependent on the invention and development of the laser, and so on and so forth. So if you can come up with a quantum information processing platform that sits on top of something that humans have already spent $1 trillion developing, you'll be in a better situation than otherwise. Okay, so what are possible? So that's our list of things we want. What physical objects can possibly fulfill these criteria? Well, I'm pretty sure this is the complete menu. If we want to make a quantum computer, it's going to be out of this stuff. But you can even look at this menu pretty much from the get-go without having too many discussions and say, I'm allergic to most of the stuff on here. So the complete reasonable menu is much smaller. I don't know, I'd be happy if anybody wants to object to the crossing out of any of these elements for quantum information processing. I don't even know what the closest call is, maybe the muon, but I don't think any of these are a particularly close call. So if you want to make a quantum experiment that's interesting in a quantum mechanical way, it's going to use this restricted reasonable menu and combinations thereof. So we have photons, we have electrons, and we have up and down quarks. So I want to say a little bit about a few of these individual elements and then combinations among them which is this slightly idiosyncratic, but I think a reasonable way to kind of organize the different types of effort in quantum information processing or in quantum experimentation in general. So probably the first thing you would try if you wanted to do something interesting in quantum mechanical with some element of that menu is the photon. And photons are great. They have spin. They're easy to control. There's some frequencies where humans have gotten really good at controlling them, notably the near infrared and the microwave regime. And we can generate these. We can transport them over very long distances. We can detect them with high efficiency, and they're very well isolated from everything else because of the linearity of electricity and magnetism. And I'm trying to, as I go through these, by the way, I'm going to highlight members of our collaboration who have particular research interests that are relevant to the thing I'm talking about. So some of the engineers within our collaboration are really good at developing tools to do these things with photons. And the red name, by the way, just so my convention is clear, is the one associated with the picture that I'll put at the lower right of each slide. The drawback here is, of course, in achieving nonlinearity, because the equations of electricity and magnetism are so linear. Making a 2-qubit gate is pretty challenging. People, work on doing this with single photons, making transistors, but it's a serious technical challenge. The loss parameters and so on are relatively challenging for scaling, I would say. In the microwave range, there are tricks you can do to get strong inharmonicity and nonlinear interactions, and that includes actually Josephson junction-based quantum computers, which I'll talk about a little later. All right, so that's photons. Electrons, I think, are another really intrinsically appealing system for doing quantum information processing. They're sort of what you imagine when you imagine a spin-a-half system. They're stable, they're everywhere. They have this nice monopole moment and a mass, so they don't run away at the speed of light. However, even with that mass, you need some way to keep electrons around to do an experiment with them. And as an atom trapper, the way I tend to classify different types of experiments is by how they trap the thing that they're working on. So you can trap electrons, of course, in semiconductor nanostructures or metallic nanostructures. And this is actually a lot of exciting work in this area is going on right now in quantum information processing. A little bit more exotically, you can trap them on the surfaces of superfluids. David Schuster has been doing experiments along these lines for a while that I think are beautiful and interesting. And you can trap them just like you would trap an ion in a Paul trap, for example. And down at the lower right, you can see some images from a recent paper by Hartmut's group. And I guess I don't come back to this later, but I'll say that as I look across this whole range of quantum information processing architectures and think about the ratio of promise to investment in each area, this seems to me to be one that has a high ratio of promise to investment. So I think, I don't know, Hartmut will maybe tell us about this in a future colloquium, but I think this is pretty exciting work for possible future quantum information processing platforms. All right, moving up our menu to up and down quarks. Well, it's not going to work to use them on their own, so you can bind them together into nuclei. Of course, nuclear spins are a very well explored quantum information processing platform, going back to the liquid state NMR work quite a while ago now. And nuclear spins are great. They're nice and isolated. There's actually a group of people at my campus, UC Santa Barbara, who are thinking about whether nuclear spins carry quantum information in biological context, which is a very exciting prospect. I don't know if it's accurate or not. But if you're thinking about making a quantum information processing platform out of nuclear spins, at least in the liquid state, often what you run into is challenges with state preparation. Separate from the spin, of course, nuclei have their own catalog of excitations. You can think of them as little atoms. And in principle, one that offers a whole menu of a whole Hilbert space that you could use for quantum information processing. That's, I think, very far beyond current human technology. So if you want nuclear physics to look like atomic physics, you need to have gamma ray lasers that look like our visible and near infrared lasers. And we don't have those. But if we did, I think this would be a very appealing possibility. That's not something that's going to happen on the life scale of this institute, but maybe in the far, far future, this is an interesting possibility. However, I will say that if you're not aware of it, I recommend you check out Eric's work on thorium-229, which has a transition which is much lower energy than a typical nuclear transition, which could be a very interesting tool for future, especially for quantum metrology. Okay, now we've talked about photons, electrons, and hadrons. Now I want to talk about combinations thereof. So if you take electrons and hadrons and squish them together, a popular thing that you can make is an atom. And these are more complex than the individual particles we've been talking about so far. They have internal structure, hyperfine structure, and so on. And this gives you some new tools. You have better tools of quantum control. You can do optical pumping, laser cooling, things like this, using the internal structure. But of course, you can also kind of get lost in that structure, and the additional entropy can be a curse as well as a blessing. A lot of the effort within our Challenge Institute is concentrated on atoms, not all of it, but a lot of it. And I've organized this effort in the list below by how these atoms are trapped. So from the strongest to the weakest, if you want to use an atom for quantum information processing, you can trap it with a chemical bond. So an example of this is the nitrogen vacancy centers, which are used by Norm and Anya, for example, although those are really more like molecular ions than atoms, but we'll let that slide for the moment. Or donors in silicon, also a very important class of quantum information processing architecture that looks like an atom, but it's trapped inside a solid matrix. And that's a very tight trap, so everything can happen at very high energies, and it doesn't ever run away from you. That's nice. On the other hand, it reduces the isolation to have such a tight trap. You can trap atoms on surfaces. Actually, 3 members of the CIQC have a collaboration thinking about this and how you can probe and interact with atoms adsorbed on surfaces of diamond. And this is also something that Wes's group is thinking about in a somewhat different context. Then you can trap things using their monopole moments. So that's, I'm referring to ion trapping there. Atoms, you take away an electron, or I suppose you could add an electron, create an ion, and use that as a handle to hold on to it. And Hartmut and Eric and Wes all do beautiful work in this area, and we'll presumably talk about that at a near future CIQC colloquium. Finally, you can use dipole moments. If you don't rip an electron off the atom, but leave it in its happy charge 0 state, it still can have a dipole moment or an induced dipole moment, and you can use that to manipulate it. And that's kind of the technology that Dan and Manuel and I use. And shown at the lower right here is a strontium mott inside Manuel's apparatus down at Caltech. Okay, moving up to sort of more and more complicated combinations of standard model particles, you can take these atoms and stick them together to make molecules. And these are, still another hierarchy of complexity, to the point where the experiments are getting hard to do the pumping and the cooling. But a molecule, a single molecule, until it gets very big indeed, is still a perfect and identical object in the same way that an atom is. And the UCLA team members do a lot of interesting work looking at expanding the range of capabilities that we have with trapped molecules. So this offers, I think, you couldn't argue against the assertion that this is a major frontier for quantum information processing using molecules. There's this potentially large and rich internal Hilbert space that you can explore and use in addition to the external degrees of freedom. On the other hand, there's a lot of challenges here. Nobody, as my colleague Dave Patterson is fond of saying, nobody has ever put a molecule with more than 2 atoms into a single quantum state. So this is a field that's extremely promising, but is sort of still climbing the ladder of the control techniques that have already been demonstrated for the previous elements I listed here. Now, of course, you can take those molecules and jam more and more of them together. And once you get a thermodynamically large number of them, you have a solid or a liquid, and thus, a lot more complexity to the point where if you're making a crystal, of any reasonable size, there's no sense in which it can be thermodynamically perfect or identical to another crystal. So you have to give up some of the symmetry that you get from working with individual atoms. On the other hand, solids and liquids offer collective degrees of freedom, which can be extremely powerful for quantum information processing. Maybe the most important is superconductivity, which is of course critical for Josephson junction qubits like those that Institute affiliate John Martinez uses. And other collective degrees of freedoms offer interesting possibilities that different groups are exploring, mostly not within the Challenge Institute, like mechanical excitations or magnetic states and so on. And finally, last but not least, emergent excitations within solids can actually have properties that are not found in the standard model. So it can generate new menu items, basically, for us to play with. And the most famous example of this is the non-abelian anyons that are under serious consideration by a number of Challenge Institute members and a large number of other people as topologically protected qubit candidates. Okay, so I think that concludes my lightning overview of all quantum information processing architectures, and probably I forgot one or two and offended some people, so let's let that generate discussion in the chat or after the talk. I did want to say something before I get onto the second part of the talk about the role of what I work with, which is, or what a number of us within the Institute work with, which is trapped atoms in the gas phase, not trapped by chemical bonds or sticking to a surface, but trapped in a vacuum, basically. So where do these fit in to this architecture? Because this is a major focus of effort within the CIQC, and I think it's worth thinking about the strengths and weaknesses of these approaches with respect to other ones. So trapped ions are an extremely well-established leading gate-based quantum information processing platform. There are many companies founded based on this. And I won't say more about that because I assume that Hartmut or Eric or Wes is going to tell us all about that in a few weeks. Then for neutral atoms, tweezer-trapped atoms using Rydberg interactions are not quite as old, but also, in my view, extremely promising as another kind of gate-based quantum information processing platform. You can imagine making a computer out of these. And again, I don't want to say too much about this because it's not my personal area of expertise, and I'm sure Manuel is going to come and tell us all about them pretty soon. So one thing I will say, though, is that there's a sense in which using Rydberg states interpolates between the virtues and drawbacks of neutral atoms and of trapped ions. A Rydberg excited atom is almost an ion, just within a small distance of being an ion. And as a result, it has stronger interactions, but with other atoms, but also with the environment. So there's kind of a continuum among these three approaches, I would say. Finally, the thing that I work on mostly in my group, along with Dan as well, is atoms that are neutral and trapped in a lattice and not in Rydberg states. And these are the kind of the most isolated of all these different flavors of trapped gas phase atoms because they interact so weakly with everything else. For a similar reason, they're the coldest, and you can get the most of them jammed into one place. So those all, I think, could be thought of as benefits. On the other hand, we have the weakest control over them for all the same reasons. Their evolution is the slowest. And it can be difficult to control them on an individual level because there are a large number of them. However, the invention of the quantum gas microscope in the last decade or so has been something that's enabled the individual control to actually get more of a foothold in the space of large number of neutral atom lattice experiments. In some sense, I think this architecture is not as well suited to gate-based quantum information processing the way that trapped ions or Rydberg interacting tweezers are. Although you could say that there's some massive parallelism that one could try to take advantage of in an optical lattice because you have more atoms. I think what this platform is probably better suited to is something more along the lines of a NISC-era quantum simulation experiment. And in particular, here's where I want to start connecting to Norm's introduction and talk about dynamics.
David, can I ask a question?
Please.
So what do you mean by contact interactions here?
Oh, I just mean not Rydberg interactions. So typically a neutral atom experiment is operated at such low temperatures that the only interaction is S-wave scattering between two of the atoms. The dipole-dipole interactions are typically very, very weak. And so the main thing that you have, the main channel for them to interact is just by S-wave scattering. And that's often a tunable parameter.
Right,
so,
okay.
Yeah, no, good question. So I'm basically contrasting that to Rydberg interactions, which are much, much stronger but which also open a channel to the rest of the universe, which can cause decoherence.
So dipolar or non-dipolar, basically.
Yeah, I guess so.
Okay.
Of course, atoms can have dipole moments, even if they're not Rydbergs, but it's much, much weaker.
Right. Okay, thanks.
So yeah, I think so. This is mostly where I want to kind of start talking more about what Norm was discussing in his introduction, which is the idea of using dynamics experiments, and I'll get to that in the next slide. But I think there are also some other possibilities that I'm not going to talk about so much. For example, can you use this as a platform for prototyping some techniques of decoherence mitigation? So some ways that people struggle to deal with decoherence, and that would make a topic for another interesting colloquium discussion, I think, include, engineering baths and driving in particular ways. And some of these techniques, I think, are pretty well suited to prototyping on a neutral atom platform in ways that you could then implement on gate-based architectures in the future. All right, so that was kind of the first part of the talk. And I gave this very extremely high-level overview of quantum information processing platforms and where neutral atoms fit. But now I want to talk, engaging more with Norm's topic in the introduction and talking about these next three questions, which have to do with problems that we can address, particularly in the NISQ era, using neutral atoms. And these are going to be in the area of dynamics. So I think what I would say, and I think this is true of a subset of the types of non-equilibrium quantum dynamics that Norm gave us this nice periodic table of, is that following the non-equilibrium quantum dynamics of a many-body interacting system can be both hard in the sense that we mean when we talk about quantum information processing, and can be interesting. And I think in many situations, as Norm said, even in a linear spin chain, but certainly if you move beyond linear spin chains, some form of quantum supremacy can be relatively straightforwardly attained by taking quantum mechanical particles and jostling them around a little bit. What do I mean by the quantum supremacy statement there? I just mean that it would be very hard with a classical computer to calculate specifically what is going to happen. So I think Norm said more eloquently than I do here, the possibilities here, but one thing that one has in one's mind that might be interesting to discuss among the different elements of our Challenge Institute is the possibility of generalizing the idea of which boson sampling is an example, which is to say, oh yeah, Umesh.
Yeah, sorry. Let me ask for clarification on that, David. So when you say it would be hard to calculate, is that in the same sense that it would be for a chaotic system, or is it in a different sense?
So often these can be. Oh, you mean a classical chaotic system?
Yeah, exactly.
I think that it can be harder. The problem is not so much sensitive dependence on initial conditions as largeness of the relevant Hilbert space. But let me see if Norm has anything smarter to say about that question.
I think that's kind of actually, it's sort of almost exactly what I would have said. I'm not sure if it quite addresses Umesh's question, but I agree with the answer.
But is there some evidence that it is the largeness of the Hilbert space, or is that speculate? So what's the status of that?
I think that it's speculation. And I think mainly one of the things that I want to say is that this would be an interesting topic to discuss between these two pretty disjoint communities within our Challenge Institute.
Yeah,
so
no, that would be great.
Yeah, so I know I don't claim that I know this to be true for sure.
Yeah.
But I'm sort of asserting it here as a provocative topic for discussion. Okay, so what I want to do mostly in the rest of the talk, which I guess I should. When did I start, Norm? 12:30?
Yeah, I think you have maybe about 20 minutes left or so.
Okay, it should be fine, actually. So I want to discuss some dynamics experiments that we've done in my group, and other very interesting dynamics experiments have been done in other groups within this institute, with an eye on those three questions I put on the previous slide. Can these be springboards or inspiration for future dynamics experiments that actually we could think about addressing quantum hard problems and answering questions that were both challenging and interesting. So one thing to say that I'm very confident of is that neutral atoms are a nice and flexible platform for studying non-equilibrium quantum dynamics. So I'm not going to talk about any of these topics, but these are some of the recent things we've explored just in my group, and other topics have been explored in other groups of people on the call recently in the area of non-equilibrium dynamics. So ranging from band engineering by driving to looking at pre-thermal states of matter. These are the data that Norm showed in his introduction, which I would say are dynamical. To driven quasicrystals, kind of exotic symmetries of driving, to actually making analogies to ultra-fast science and looking at dynamical evolution on timescales that are very fast compared to the relevant timescales of the system under study, to synthetic relativistic evolution, to this recent study I put in the lower right of very slowly driven lattice systems. Slowly means roughly at frequencies similar to the Bloch frequency, where we see the character of transport depend qualitatively on the topology of Poincare orbits in the system. So I won't talk about any of that, but just offer it as evidence that there's a lot of different things you can do. And to me, this is exciting from the point of view of our Challenge Institute, because it means that, you know, we can kick around ideas, try to come up with a problem that we all can agree is hard and interesting, and then hopefully it could actually be realized in experiments within the Institute, which I think would be a great outcome. So the two things I am going to talk about sort of quickly here, just as examples of pandemic aerodynamics experiments that we've been doing in my group, are the quantum kicked rotor and the kicked Aubrey-Andre Harper model. So first, the quantum kicked rotor. So the quantum kicked rotor is a very old topic in atomic physics, and before that in classical chaos. And it's really this central prototypical example of classical chaos and the quantum version of classical chaos. So the Hamiltonian is very simple. Classically, I put it up here. It's just, you know, you can think of this as a rigid rotor, a pendulum, which can spin all the way around rigidly, and you're kicking this by turning on and off gravity very rapidly with some strength and some period and some frequency. And classically, if the kick strength is large enough, this is a system that heats diffusively. So these classical phase diagrams down here show for different k, which is the kick strength in this Hamiltonian, that the orbits go from being periodic to being chaotic when k gets bigger than about 1. So this is really obeys something called the Chirikov standard map, and it's a really nice analytical test bed for studying classical chaos. Quantum mechanically, something totally different happens. If you take the same system and quantize it, it does not heat diffusively as a chaotic classical system does, but rather localizes at finite energy and forever stops absorbing energy from the drive. And this is something that's been studied using atoms for a long time. Actually, maybe even the earliest, or certainly one of the earliest optical lattice quantum simulation results, I would say, was Mark Raisin's study of the quantum kicked rotor using rather hot sodium atoms in a pulsed optical lattice. And people have looked at different aspects of this in the years since. But what people have not really looked at is what happens if the system is not non-interacting, or more felicitously put, what are the effective interactions on the quantum kicked rotor? And this is something that we started investigating at the urging of Victor Golitsky from the JQI, who's pictured at the lower right. And we've been talking a lot with Deep Gupta's group, who's pictured on the left there at the University of Washington, because it turns out that Deep's group is sort of convergently investigating the same topic using a very complementary tool. So we've been working on this together in a way that's been kind of nice. So what we do to look at the quantum kicked rotor is we take a Bose condensate of lithium-7, and we apply a periodically pulsed optical lattice. So that just means we have our little blue blob of a BEC here, and we turn on this lattice for a few hundred nanoseconds every few microseconds, and then we keep doing that. And this, if you look at that classical Hamiltonian on the previous slide, this is basically a quantum mechanical realization of that same Hamiltonian, with the lattice supplying that cos x term and the strength of the lattice being the strength of the kicking. And what we observe if we do this, oh, and by the way, we can tune the interactions because we have a nice Feshbach resonance in this atom. So we can tune them to 0 or kind of arbitrarily strongly attractive or repulsive interactions. And what we see if we do this is a lot like what Mark Raisin saw these many years ago, which is that the atoms do not infinitely absorb momentum from the drive, even in a classically chaotic regime. So this is like a stroboscopic picture of what the atoms do as a function of kick number. And you can see momentum is on the y-axis because this is the time of flight picture. So you can see the momentum increases as time goes on, but at some point it just stops increasing and the atoms are in a steady state. So even though we're whacking them continuously with a lattice every 5 microseconds or so, they stop absorbing energy. And this is a purely quantum mechanical phenomenon, which would not occur classically. You can recover the classical behavior if instead of kicking periodically, you apply some jitter to the kick timing. And that's what we've done for the black points on this graph. So now I'm plotting the energy as a function of kick number. For the red, that shows the data on the previous slide. You can see the energy grows in the initial few kicks, but then saturates at some value as the system localizes. But for the random kicking, the energy grows more or less without bound as it would in the classical case. And we see a pretty good agreement with theory. So you can do, and by the way, interactions are turned off for all the data that I've shown so far. So if we turn off interactions, we can follow it just by integrating the time-dependent Schrodinger equation, and we see that we're getting a nice clean realization of the kicked rotor model. Even though our lithium atoms are actually in 3 dimensions, we're realizing this one-dimensional Hamiltonian fairly nicely, as is shown by the agreement between experiment and theory on these plots. And the plateau at which it localizes depends on the kick strength, which is what's happening for these red, green, and blue points on the right-hand graph. The final point before introducing interactions, which is the actual new element here, is that this physics, the localization physics here, is robust to the momentum spread. You do not need a BEC to see this physics. So what's shown here is Rabi oscillations doing a Ramsey experiment with just 2 kicks. And you can see the Rabi oscillations decay with some time of 100 microseconds or so. And it turns out to be the case that we can follow the localization for times way beyond that. So this is something that happens to every single momentum state. It's not affected by some spread in momentum states. And the spread in momentum states, I guess I should have said, is exclusively responsible for this decay time. There's no other decay phenomena here that we can measure. So the next step is to add interactions. And so we did the same experiment, but used the Feshbach resonance to tune the contact interactions. And so Victor was motivated to urge us to do this because he felt like there were 2 possible outcomes. You could see delocalization, or you could see many body dynamical localization. And he viewed this as kind of a win-win because either one is sort of interesting to see. There have been theoretical predictions in this regime, but they pretty much all use a mean field approach. And the validity of that is not clear in this context, where the relevant physics involves collisions between atoms and violent redistribution of momentum. That's not the kind of phenomenology which is very well captured by mean field approaches. So we did the experiment, and these data are still kind of being figured out. I think the data I'm showing here are just a few weeks old, but the preliminary observation is that we see a pre-thermal plateau. Again, the top plots here are plotting energy versus kick number on a log axis on the left and a linear axis on the right. So we see this pre-thermal plateau for all 3 interaction strengths, which is non-interacting in blue, medium strength interaction in turquoise squares, and stronger interactions in the diamonds. Apologies for the different colors on the 2 plots. And we see that as we turn on interactions, we see after a pre-thermal plateau some delocalization phenomena that starts at a time that depends on the interaction strength and maybe has a slope which depends on the interaction strength too, although that's a bit less clear. This is sort of the main result of this, is that we can observe this nice delocalization. It would be very interesting to compare this to the predictions of mean field models and see if we're going beyond what people can calculate in those ways. But that's sort of future work for us at the moment. There's a few other things that are interesting that you can explore here, including the effect of time reversal. So you can pi phase shift your kicks and sort of reverse the momentum space evolution. So that's what's shown here. you can see the momentum evolution grows for the first 5 kicks, and then we reverse and come back, and we get a lot of the atoms back to the original 0 momentum state with some imperfection. And I think studying those kind of phenomena as a function of interaction strength offers some interesting possibilities. You can also study, maybe I didn't go into enough detail to talk about this, but you can study fractional resonances or resonant phenomena in this system, and we can see resonances with kind of some somewhat peculiar denominators in the behavior of the energy as a function of the kick period here. Finally, the interactions don't have to be repulsive. They can be attractive if you jump over the Feshbach resonance, and these experiments are fast enough that we don't run into collapse phenomena. So there's some interesting possibilities there for studying the effect of cohesive interactions on physics like this. Okay, so that's the first kind of recent dynamical research that I wanted to talk about to seed discussion of future possibilities. The second one I'll talk about more briefly, which is periodic quasi-periodicity. So in the quantum kicked rotor experiments we discussed, it's kind of maximally simple. You kick with a lattice, and then when the lattice isn't on, the atoms are in free space. They have quadratic dispersion. It's all kind of maximally simple. So it makes you think whether there might be richer possibilities to study here in a similar kind of kicked matter context. And one possibility is the kicked version of the Aubrey-Andre-Harper model. So what we imagine here is a lattice, ordinary lattice that's on all the time, but it has a pulsed perturbation, which is incommensurate with the lattice itself. So the static version of this Aubrey-Andre-Harper model, which is sort of a one-dimensional model of the integer quantum Hall effect, exhibits a well-known localization phase transition. And this also can be considered as a one-dimensional version of a quasi-crystal. So this picture on the left is a picture of a quasi-crystal, as you can tell from the 5-fold symmetry. In the middle is kind of a cartoon of the type of lattice that we use to do these experiments. So this is a bichromatic potential, which has 2 frequencies in it, which are of incommensurate wavelength. And it's well known, and this is old data from a paper of ours from a few years ago, and people have seen this before as well, that there's a localization phase transition at some value of the quasi disorder in this kind of bichromatic potential. So the new thing that we've been trying recently is to realize the Aubrey-Andre-Harper model, the kicked Aubrey-Andre-Harper model, using a pulsed bichromatic potential, which is really a dynamical context in which to study the physics of localization that's studied statically in the data shown here. And our preliminary observation on this experiment is that, as predicted by theory, the kicked Aubrey-Andre-Harper model does exhibit a period-dependent localization transition. So what's shown here is the expansion rate. So red is delocalized and blue is localized as a function of the kick period, t. Sorry for the poorly labeled axes, but t is proportional to the kick period on the vertical axis, and lambda is proportional to the strength of the quasi disorder on the horizontal axis. And the red line is where you expect a transition from a localized to a delocalized state. And we really kind of are seeing this, and these data are even younger. These are just a few days old, in fact. So this is still preliminary and being worked out, but we do seem to see that if we go to longer periods, we actually break the kicked Aubrey-Andre model and start to access multiband physics, moving beyond a tight binding approximation. So that could be thought of as a bug or a feature, depending on your inclination. So that's what I wanted to say quickly about like our current work on dynamics as a possible seed for future ideas. And I wanted to also put up this slide with some other thoughts on future CIQC relevant dynamical experimental possibilities. And this is really the fruit of a discussion that Dan and Wes and Ehud and I had in our capacity as members of CIQC Working Group 11 earlier this week. It's a truism that a quantum computer is a nonlinear interferometer. It's in general how you can consider any gate-based quantum information processing architecture. And then in a neutral atom context, you can think about trying to do experiments that involve evolution in some tunable network of nonlinear interferometers. And I think it's pretty clearly true, although open to questioning of this, that studying the evolution of bosons or fermions in a tunable network of nonlinear interferometers is hard. I mean, boson sampling is a special case of that, I think. As to whether it's interesting, that may depend on the deeper question, but that's something that I think would be fun to discuss among different members of the collaboration. In the experimental context we're talking about, our control is imperfect, but our gate depth is large. So that's the regime that we can sort of access today with neutral atom experiments. And so some of the graphics at the right here show evolution through a network of beam splitters in a band structure. That's the top graphic here. Those are data from our lithium experiment. And then showing that we can tune the properties of an individual Landau Zener beam splitter. That's the middle graphs here. The left is theory and the right is experiment, matching theory reasonably well. And at the bottom is
sorry,
just
David.
yeah,
Can I just ask quickly? So could you just say, you know, with this imperfect control, can I think of it as n number of qubits and depth this much, or what? How should I think about it if I want to have a mental big model?
I would think about it as putting some imperfectly controlled initial state through a very well controlled network of nonlinear, potentially nonlinear beam splitters. So I think where there might be some challenges for us is in setting up the right initial state. But so there may be some randomness or non-repeatability there. But I think neutral atoms are pretty good at making beam splitters of various generalized kinds, and large networks of them and propagating through them.
So what should I think of n as, the number of qubits and the depth? What parameters should I think of?
Well, the number of atoms in these experiments is typically 100,000 to 1 million. The depth is, I guess, the number of beam splitting operations you can go through before you get to, during one coherence time. That depends on the details of the experiment you're doing, I think, but I think it could be competitive maybe with modern boson sampling experiments. I think Ehud maybe has some response as well.
Well, actually, a question: why do you say it's nonlinear? Quantum mechanics is linear, unless you have measurements on the way. But
oh, I just mean you could add interactions.
Okay, but it's still linear. Just interacting.
Okay.
It's linear in a huge space, but it's linear. Yeah.
That's okay. I see your point. Yeah. By nonlinear, I mean in the sense that if you had two photons going through a beam splitter, they don't interact with each other at all.
Yeah. Yeah.
But we can, in the context of neutral atoms, you can actually turn on interaction.
It allows entanglement rather than.
Yeah. Yes.
Yeah.
Well, but you can do. Yeah. Okay. I mean interacting. I should probably just say interacting to be clearer. Yeah. So I think the answers to Umesh's very good question depend on the details of the experiment that we're actually talking about here, and there's a few different possibilities. So like this top data has to do with evolution in a band structure, and the beam splitters are in a band structure. What Ehud and Dan and I were mostly talking about, and Wes, was evolution in a real space lattice. So that's something like this cartoon at the bottom here, which is just a calculation, obviously, of an evolution in an interesting kind of network that has not been explored very much experimentally of a quantum gas. And this constitutes basically a large number of Mach-Zehnder interferometers all connected together. So depending on what you're doing, I think you could access different regimes. And there's some other possibilities we came up with that I think are seeds for discussion. Suppose you have just some general system, let's say of bosons that are interacting, and you want to evolve them in time and solve in some way that's hard to calculate. A possible way to pose that sort of problem that we discussed a little bit the other day is to realize an inverse problem. So to say, I want to create an initial condition that under this Hamiltonian evolution will evolve into a picture of norm. This is potentially very challenging unless you have the ability to reverse the time of your simulator, in which case you could just put in a picture of norm and let the system do what it will with that, and then take the state after some time, give that to somebody and say, if you run time forward, you should get norm back. So I don't know, that's a pretty, I've talked about that idea now for longer than we've all thought about it together, I would say, but it's a seed of possible future ideas. Yeah, so there were some ideas based on the sort of classic topic of optical lattice quantum simulation, which is a Bose-Hubbard model. And a tool that I didn't talk about here at all, but which is relevant, especially for some of the questions that Hood had, is quantum gas microscopy. So if you have individual site resolution, you can do a lot more interesting things with these type of experiments than if you're taking average measurements. I think I'm sort of running out of time. So I'm going to just whip through these questions that Charles gave me to answer. And maybe we can talk more about them in the discussion section. So if I could assign a team to work on a different problem than what I work on, and I was sure they would succeed, I would have them build a gamma ray laser that was totally tunable across the whole gamma ray spectrum. But since that is impossible, probably one of these other things. And actually, we are thinking of putting together a tweezer experiment. And I know the Berkeley team is as well. And of course, Manuel has beautiful tweezer experiments in Caltech. The next step to progress, I guess the thing I have in my mind here is pictured at the lower right. So there were analog computers that were very important that were used for fire control on naval warships for a long time up through the end of World War II. And I wonder if there might be similar special purpose quantum hardware that we can think about developing within the CIQC, short of a Turing machine, but solving problems that are not only hard, but also useful for other things. Near-term results and potential downfalls, I guess I answered potential downfalls. I think some of these ideas really do require the kind of collaboration between different tribes and different communities that hopefully this Challenge Institute will enable. Yeah, I guess I think a big challenge here is mapping the things that are feasible in atomic physics experiments to problems that are truly of interest from the quantum information perspective. So I hope that's possible, but I think it's an open question and something we can all discuss. And then, okay, so there's this prompt to have an unconventional or strange idea. And I put a few here. Some ideas for new approaches to quantum sensing, including using trapped atoms. I think tweezer experiments with small BECs that are not Rydberg interacting, but just interacting with contact interactions might make a nice test bed for exploring quantum heat engines. And finally, here's a super strange idea, probably crazy, which is that every object is, in some sense, simulating its own properties continuously. And I don't know if this is even a well-posed question, but that must be harder for some objects than others. And I wonder if the variable difficulty of that calculation has any observable consequence. Let me thank my group members. This is unfortunately a very old picture. There are new group members since this was taken, but many of these people are still here. The people who supported the research, including this new and slightly blurry CIQC logo, and all of you for your attention. And let me turn it over to Norm as the Master of Ceremonies.
Thanks, David. Super, actually, both parts were super interesting. I really enjoyed it. There are quite a lot of questions. We won't get through all the questions related to talk before we move on to the discussions, but let me ask a couple of them. Bubakar asks, you had mentioned that it's pretty challenging for molecules with larger than 2 atoms to get to prepare the system in a pure quantum state. What are the fundamental reasons for this challenge?
Okay, great question. I mean, one standard thing that people talk about is the absence of cycling transitions. So the fact that we have such good control over atoms, it's really amazing what people can do with atoms in the gas phase. You can not only put 1 million atoms all into the same internal quantum state, exactly the same one, you can put them all into the same external quantum state. So they have all the same quantum numbers. And the ability to do that really relies on laser cooling, which relies on the existence of a transition that you can drive 100,000 times without the atom leaking into any other state. That kind of thing really doesn't exist for most molecules. So you drive it a few times and it goes into some other state. And it's really a consequence of the much larger state space of molecules as objects. So a lot of the control techniques that people are developing for molecules are ways to get around that and sort of tools for navigating in this much larger space of possible states, which is also, you know, a superpower for molecules if we can get around the technical difficulties it imposes.
Right. Good, yeah. So Francisco Machado had a question, actually directed to both Umesh and David. I guess it sort of builds off of Umesh's question from a little while earlier. So just thinking broadly about this question of kind of chaos and computational cost, does one have any sense that the absence, in classical systems, there's this KM theorem, and in quantum systems, there doesn't seem necessarily to be an analog. Is there some way to sort of, is there some consequence of not, or of having or not having this KM theorem that should impact the computational cost of trying to sort of look at chaotic systems?
It's a very interesting question.
I'll nominate Umesh to answer first, since David is.
I second the nomination.
Actually, may I nominate your Norm to explain to me what the theorem says?
Yeah, sure. Okay, that sounds good. So the KM theorem basically says that for a classical integrable system, so if you have a small perturbation away, that certain orbits of that are stable. So in some sense, if you think about in a classical system, the transition from integrability to chaos doesn't happen like that, basically. There's some sort of perturbative stability, and that's the notion of the KM theorem. I think originally proven by Kolmogorov, and then sort of more generally, I don't remember, maybe it was Moser who did it for Hamiltonian systems. But I think the quantum mechanical, I think there's no sort of quantum analog of that. And I think
sorry, Norm, can I just ask? So the theorem says what? That there's stability, or that that you either have a chaotic system or there's stability, or
no. That's starting from an integrable system. So an integrable system where, for example, if you look at trajectories, it's really thinking about trajectories in phase space. So if you start with an integrable system and you look at trajectories in phase space, you'll find sort of periodic orbits in almost all of the integrable systems. You break integrability a little bit, and you ask, do all of these periodic orbits just disappear, and now phase space is like just like a it's haywire in phase space? And the answer is no. You still have some stability there, and that's sort of the sense in which sort of you don't go from integrability to chaos immediately. Is that clear, Umesh?
I would say that it's a lot more clear than it was before you said that. Yes.
Yeah.
Okay.
Any thoughts, David?
I mean, I think the answer to the question is probably, it's definitely that I don't know, but it may be that it's not known. There's not a general answer that's known about whether we can guarantee that something is hard in some quantitative way.
Yeah. I think it's interesting. I think, Francisco, I think it's interesting whether or not this kind of stability means it's sort of easier to get, if you were only interested in approximately the right answer, the stability to perturbations maybe makes some things easier, but maybe if you don't have that theorem guarantee you the perturbative stability, maybe it's harder in some sense. But I don't know how to sharply answer that easier either.
Yeah, no, me neither. It's a very interesting question for sure.
Okay, I'm beginning to follow the question. I don't have an answer, but so the question was asking if what's the effect of, if there was such a stability theorem for a quantum system, what would it make things easier, harder? Would it be more robust and more robustly hard, for example?
Right.
Possibly.
Exactly. That's right.
Yeah. Then that's an interesting question.
Okay, maybe one other question. So Emily Davis wonders, for the second part of your talk, David, for the time-reversed quantum kick rotor, is the imperfect reversal due to technical details or some underlying physics? And is there kind of a clear mapping from this flavor of measurement to some kind of out-of-time ordered correlation function?
That would be great. That's certainly something we have on our list to think about, the second part of the question. I think that the imperfect time reversal in this particular image arises from motion in position space during the experiment, which breaks the sort of pure momentum space evolution that you're thinking about. So the issue that we're running into here is that lithium is extremely light. That's sometimes nice and it's sometimes not nice. And here it's not nice. So this is an area where our experiments are complementary with Deeps, who's using ytterbium, which is an extremely weighty atom. So I think that's what's going on here. One can imagine, refocusing techniques that deal with that as well. But I think that's probably the limiting factor right now. It's not interactions, because interactions were turned off in these data. But I think it's a very interesting question that you raise about, I don't know about, probably not an OTOC, but maybe some analog of something that's approaching being relevant to OTOCs, being measured in a similar way after turning on interactions.
Great. Actually, David, maybe let me ask you to stop sharing your screen, and let me second Dan's request for folks to folks in the chat. If you're able to / bandwidth allows, please turn on your video for the discussion piece of this. It'll be nice to sort of see everyone. I think that'll make things more interactive and fun. And please keep putting questions in the chat. Sort of, I see them coming through. But maybe starting the slightly more broad piece of this discussion, I think our fearless leader, Dan, had a very good question, which is two very related questions, I would say. Generally speaking, kind of what aspects, and maybe this is not just for David, I think, hopefully the discussion extends beyond just David answering this one. What kind of aspects of a Hamiltonian dynamics question qualify it as a computational problem and as a candidate for establishing quantum advantage? So is it fair, I mean, folks like Umesh, Brigitte, to think about this question of, sampling from the output wave function of a Hamiltonian dynamics problem as a demonstration of quantum advantage? Or, as David said, is that not the right class of problems that one's allowed to consider?
This is exactly the question that I'm interested in finding out an answer to.
I think Adam may have thought about this question, so.
Like, one thing that you typically want to have is some exponentially large space of possible instances of your Hamiltonian evolution that you're considering. Like, if you consider depth n quantum circuits, there are exponentially many different quantum circuits. So you need some sort of input to your problem, right? Like many different inputs for a particular instance size. And while there can be instances in complexity where there's only one instance for input size and you still have hardness, that those are kind of more the exception rather than the rule. So the more natural thing is you want some family of Hamiltonian evolutions. You're trying to argue that this family of evolutions is something that's hard to reproduce.
So Adam, just to pick on, add to that. So couldn't you think of the input as being that exponential? So for example, if you were to look at a Turing machine, right, you can a universal Turing machine, you specify it using a constant number of bits, right? But then your input is the thing that provides the complexity. You have so many possible inputs. So let's say that the Hamiltonian
different states, like different initial states, could provide input. Yeah, exactly.
So is that so if one thinks about one of these Hamiltonians and one imagines time evolution from different product states, would that kind of qualify as something that one could really think about as an example of an advantage? I see. Okay, that's really nice.
Well, that one could think of that as a programmable model, right? Because you have your Hamiltonian, you specify some of the input bits, that's your program, and the rest of them are the input to the program.
Can I ask, so maybe a provocative question? I want to understand the rules of the game here, because it is really a game. The sampling problem, I'm not sure anyone proved that it's NP hard, or that it's hard to do classically, right? Well, it's NP, it means NP complete means it's not proved, but let's say I do something more useful, like I take a Hamiltonian and I simulate it, and I measure in the end just a single number, like the diffusion constant of this system, because it has some diffusion constant. That is, of course, something that is intrinsically due to some very complicated quantum evolution, and most likely there is no way to calculate it in any other way.
That's very interesting.
So why would that not count as showing quantum advantage? Because that also you cannot prove that I can do efficiently.
Well, I think the issue is what you can, I think the issue is in that case, you have no idea, if you do have some way of saying, here, I can show you in the following model that this is really a hard problem, then you would have taken a step towards showing, well, yeah, that's quantum advantage. But for random circuit sampling, we have various kinds of, complexity theoretic proofs saying, here, and if you look at it like this, here's a hard problem that's embedded in there.
Like to kind of chime in, like the complexity theory always requires some input-output relationship. So if you have to have the things that makes things hard is connecting the different output values with the correct input values, right? So if somehow you have some system and you just want to measure what's the diffusion coefficient, and there's no even notion of an input because it's some asymptotic n tending to infinity quantity or something like that, there's no notion that we have necessarily to formalize why that would be hard, because there's some number you're trying to get your estimate for. There is some classical algorithm that just outputs that number. It just does nothing but outputs the number, right? So there's always an algorithm.
No, there is an input.
There's not always an algorithm that associates the correct number with the different inputs, right?
Yeah, there is an input. So if you want, input are the parameters of the Hamiltonian, for example, and the say temperature of the initial state, or energy density of the initial states. So there are inputs. And yeah. I don't think we know how to write a classical algorithm that will input it correctly for all choices of parameters. Yeah, so there is definitely an input-output. It's only that the output is something that I can easily measure, and I don't need to measure by sampling.
Yeah, I think this is
sorry,
go ahead, Eamon.
No. So sorry, easy measurement is a positive thing here.
Yeah,
the fact that it's not that's not the problem.
Right.
I think the issue is how easy is it to compute, and what evidence do you have that it's hard?
Right. So
I only recently
maybe a bit better question would be: is there some output of quantum evolution that I could get and measure in a small number of measurements that would be sort of more computation you could prove is computationally hard, or show relations to computationally hard problems? Are there non-sampling problems like that, or
I mean, something I think about in this context from the cold atom world is the measurements of the equation of state of unitary Fermi gases, which were very beautiful and done to high precision, in the last 10 years or so, and served as input to other fields, astrophysics and so on. So it's possible to have measurements like that, even if you're measuring a single quantity, and that are hard to calculate by any other way, and that can be useful. I learned recently that even calculating the viscosity of water from first principles is, I think, an open problem. Anyway, very, very hard, but I think maybe just impossible. So I don't know if that's another way to restate what Ehud was asking about.
Well, I guess in your case, you could argue in this, maybe viscosity is harder, but equation of state, they would say, okay, you can do quantum Monte Carlo. And for any finite temperature, you can probably do it fairly efficiently. Well, maybe if you go to very low temperature, and there is a sign problem. But,
there's a sign problem, yeah.
Well, but not in this system, because it becomes super fluid, and then the sign problem again disappears. So probably you can do anything. So that's probably not a hard problem. Getting viscosity is something dynamical, and then there is always a sign problem. So basically, okay, another way to phrase it, maybe in a more information theoretic way, is that we have if there is a sign problem for sampling, even if I get a single number at the end, then is there any indication that problems that have an irremovable sign problem are essentially hard? Like getting the ground state of a system that has an irremovable sign problem. I think Hastings has some theory about this, theorem about on hardness of ground state.
No. So that's the that's on the difficulty of computing ground states. On the adiabatic evolution in the absence of a sign problem.
I see.
So that even in the absence of a sign problem, you can create hard problems.
Okay, so you say finding the ground state is a hard problem.
In general, yes, it's QMA hard, right?
But what should I measure in the end to say that it's hard?
The energy, the ground energy.
Just the ground state energy. So that's a local measurement. Well, in the dynamics, you're requiring some very non-local measurement.
Yeah.
It's not, I guess it's not clear whether or not, it's not clear whether or not that is a requirement. I guess for things that have been done thus far, it seems to be the case, but I kind of agree with you. If I input different states with different energy densities and I ask what the diffusion coefficient is, why it seems, it's not immediately clear to me why that doesn't sort of satisfy, or why one couldn't sort of say, I guess one would have to maybe work on it to be able to say statements about that. But maybe let me just in the interest of not cutting off the student and postdoc discussion, I do think that this particular question is maybe one of the ones that kind of burns a hole in my head. So I do think that it would be nice to sort of continue these discussions, but there's a couple of questions a little bit more on the long-term experimental vision that maybe I wanted to hear David's thoughts on just before we transition. One of those questions that people were asking is, there's a very broad question of scaling. And it seems like the answer to scaling that everyone kind of, I don't know, not cops out, but everyone gives is modularization. Scaling, well, we'll modularize. Is there some other perspective that you have where there may be an alternate pathway to scaling, or is there some system that might be sort of intrinsically scalable in some sense?
Yeah, that's a great question. I don't know that I have a great answer. Because you can always pretend there's little glowing wires going between, 10 instances of your experiment, but those are really, really hard wires to make.
Yeah.
So if there's another modality where instead of hooking together 10 copies of your thing, you have one copy that stores intermediate calculations in some local quantum memory and then puts those together later on, I could imagine some sort of tree-like structure like that for an experiment. That would certainly be worth doing. I've thought a little bit about quantum, remote entanglement generation lately, and it's just fantastically hard experimentally before thinking about anything theoretical.
Makes sense.
But if you think, David, if you think about hybrid systems and you use photons, right?
Yeah,
if you can bring photons in, then
it's one of the great things about photons. And
right. That's what's done in superconducting qubits. You use photons to entangle remotely. Microwave photons. Yeah, microwave photons in that case.
Right. And if you want to do something, if you want to move that to a true scalability solution for superconducting qubits, maybe you need actually to use optical photons and connect together different fridges. And that starts to be, looks awesome, but it starts to sound quite challenging also.
No, it is. For that you need transducers, and that's the problem in itself as well. Yeah.
You guys have a new colleague who's thinking hard about this and very exciting experiments.
Right. Right.
Alas.
Yes. Sorry.
Happens.
All right. That's so maybe we can end on one last question. So you mentioned this kind of buildup of sort of technology and sort of how all of experimental physics kind of builds on, industry-wide trillion-dollar investments, for example. So the question that was asked is there in your mind kind of a single enabling, or not even necessarily single, but an enabling technology? Like, is there a missing transistor for quantum computing? The question asks, could it be, is it like if you had a single photon switch, or strong photon-photon interactions, would this solve everything and we'd have a quantum computer already? What's the transistor that's, limiting us from getting a full-blown quantum computer?
Certainly if you had an optical single photon transistor with like essentially no loss. That seems like it would be a pretty generally useful object that would enable some serious advances. I mentioned gamma ray lasers kind of tongue in cheek because they're not going to happen anytime soon, but they would also be amazing. But maybe other people have other ideas. I think that's a very
it'd be fun to hear.
I'm sorry. Can I ask? David? Can I ask what would this single photon transistor look like, just hypothetically? So is it 2 inputs or 1 input, or what's the?
Well, it's a 3-terminal device, and I guess you control what happens to photon A by the presence or absence of photon B. And maybe you're using polarizations, maybe you're using rails. I guess there's different modes of photon-based quantum computing. But I think in the optical range, when you start to do that kind of thing, they all start to suffer from pretty serious loss issues. Because photons are so good at other stuff.
True. Okay, I think maybe on that wide-ranging note, let me suggest that I don't know, Dan, do you want to end with anything? But let me suggest that after Dan, maybe we'll have the PIs leave and the students and postdocs can hang out with David for a little bit longer.
Okay, well, I'll just say thank you very, very much to everybody for joining us. We will be having these quantum colloquia weekly, and I think we'll be sort of refining and evolving the use of the time as we go along. So I would love to hear input from all of you really at any moment. Thanks for that. And, just as one recommendation to everybody, get engaged in the discussion, bring in some questions, speak up, when you talk and engage in ideas, then you come up with a lot more ideas. And that's what this time is about. So thanks everybody. And I think we're gonna leave it now to the students and postdocs to have a discussion with David that's not dominated by the graybeards. So I'll tune out at this point. Yeah.
See everyone.
Thanks a lot, David.